Hi, welcome to AhaGuru question types for JEE and NEET. Every week, I will discuss one question type that is very important for JEE and NEET. And today, we are going to look at electric dipoles that are kept in an electric field. And if you move them slightly and you release it, this dipole starts oscillating. So we are going to focus on questions that involve electric dipole oscillations. Do these questions come up in JEE very often? Very, very often. Look at these questions. Okay, look at this. This is JEE 2025. An electric dipole of mass m, charge q, etc., is placed in a uniform electric field. When the dipole is rotated slightly from its equilibrium position and released, find the time period of its oscillation. Dipole oscillation question. And the question is asking you to find the time period of oscillation. JEE 2019, electric dipole is formed by etc., right? You have all of that information. It is kept in a uniform electric field. Always uniform electric field. If it is slightly rotated from its equilibrium, find its angular frequency. Well, time period, angular frequency, you know the relationship, right? So T equals 2 pi by omega. So finding this, almost the same problem, right? Now this appeared in 2025, this appeared in 2019. And look at this. This appeared in 2023, slight variation. It comprises of two charged particles. Basically, it's a dipole. One of them, right, has a mass m. The other one has a slightly different mass, half the mass. So that is the main variation. So they are separated by a distance. All of that is exactly the same as the other two questions. It is placed in a uniform electric field, okay, such that it makes a very small angle. So basically, for small oscillations, we want to find angular frequency. In this case, angular frequency. Here also angular frequency. Here time period. So you know that almost every other year, JEE is going to ask you a question based on dipoles kept in uniform electric field and the dipole is oscillating. They are going to ask you time period of oscillation or angular frequency. So knowing how to solve this question is going to be super important. And so let us focus on how to approach a question like this. Okay? Before we start looking at each of these questions, I want you to think about a dipole that has been kept in an electric field. So let us start. Here is a uniform electric field, E, that way. I have kept a dipole like this. Why will it even oscillate? Because this electric field on this positive charge is going to exert a force that way, Q into E. On this negative charge, it will exert a force in the opposite direction, right? So QE in that direction on the positive charge, QE in this direction on this negative charge, but net force should be zero, correct? Net force is zero, QE, exactly in opposite direction, so it will cancel. But does that mean that it has no effect? No. This dipole won't move, but this force and this force will make it rotate, right? It will make it rotate in this direction. And so what is going to happen? Because this dipole is not in the direction of the electric field, that is important. A dipole that is not aligned in the direction of the electric field. What will happen if it was aligned in the direction of electric field? Then this force and this force will be in one line. Therefore, it will just stay in equilibrium. But when it is not aligned with the electric field, it feels a torque. So it is going to turn this way. And it will overshoot and come this way. Now think about it. This force and this force, what will it do? It will try and turn the dipole back like that. And now again the torque will try, right? This force and this force produces a torque. It will try to turn it this way. So it will keep on going back and forth. That's why you have dipole oscillations. How do we find out the formula? Well, we know the formula for the torque, right? If I put the electric field here and I say that the dipole is inclined at an angle of theta to the electric field, so this angle will be theta, we take it in this direction, that is theta. Okay, the torque formula, you already know. What is the torque formula? P cross E. P is Q into D. Q into D, that is the dipole moment, cross E. P cross E will be pointing in the direction going into the board, which actually tells you that the torque is this way, which is exactly right now. You know the torque. In this position, the torque will be like this. When the dipole is pointing that way, the torque will be in the opposite direction. So for this position, let me write the torque on the dipole formula. Tau is equal to P cross E. Now what is P cross E? P into E into sine theta. P into E into sine theta. Okay, so let me write it down. PE sine theta. What direction? It will be this direction. But since theta is this way, we will take this as the positive direction. We are going to consider this direction as the positive direction. That is the theta direction. So this should be called minus PE sine theta, because if you see it's in the opposite direction. Minus PE sine theta, that is the torque. And we know tau equals I alpha, right? You know this formula, tau equals I alpha for rotation. This from the 11th standard. So if I basically use that, I can write minus PE sine theta, that is the torque, must be equal to I alpha. But what is alpha? D square theta by dt square. So I d square theta by dt square. So if I now look at these two, I can write d square theta by dt square is minus PE by I into sine theta. But remember that this theta is small. Theta is small. And when theta is small, we know that sine theta is approximately theta. Of course, we are taking theta in radians. So I can just think of this as theta. So minus PE into theta divided by I. So we can write d square theta by dt square. Common convention is to write this as theta double dot. Theta double dot. That means 2 times you have differentiated with respect to time. Dot always represents differentiation with respect to time. So theta double dot is minus PE by I theta. This actually looks like a formula you probably know. For simple harmonic oscillations, x double dot is minus omega square x, right? That is the basic rule for simple harmonic motion. This is the equation that we are going to use. So here, theta double dot is minus something into theta. This something must be omega square. So omega must be root of PE by I. Omega must be root of PE by I. What is I? I is the moment of inertia of this dipole. Moment of inertia of this dipole. How do we calculate the moment of inertia of this dipole? About the center, this one has some mass m1. m1 into this distance square plus m2 into this distance square. Won't the distances be equal? Yeah, this will be d by 2, this will be d by 2. All that we will do when we actually get to the problem. The point is you can find the moment of inertia I. And you know how the dipole moment can be found, right? Q into D. So that will be the dipole moment. So dipole moment into E divided by moment of inertia, root of that, that is going to be omega, which is the angular frequency of oscillation. And time period is 2 pi by omega. So 2 pi root of I by PE, right? You just take the reciprocal of that. So basically if you get this, you get that. And for that, you have to write this equation. This is the important equation. Torque is equal to I alpha with the correct sign. Okay, so torque will be opposite to the theta direction. So therefore you get that minus sign. You put that in carefully, put the assumption that sine theta is close to theta because you're talking about small angles. With this formula, we will be able to solve all of these JEE questions. So this whole thing you should definitely know. And once you know it, when you actually look at a question which involves dipole oscillations, it is very, very straightforward and simple. Let us now look at this question that appeared in the JEE in 2025. An electric dipole of mass m, charge q and length L is placed in a uniform electric field E, which is E naught I cap. When the dipole is rotated slightly from its equilibrium position and released, find the time period of its oscillations. Now, this question is not very clear, okay? They say that the dipole has mass m, but actually you need to assume that each of the particles of the dipole has mass m. This has mass m, this has mass m. Generally, when it is mentioned that dipole has mass m, it means the total mass of the dipole is m. So you'll have m by 2, but that is not what is expected here. Remember, JEE will not be very precise, okay? So you have to keep in mind that when they are talking about a dipole of mass m, charge q, well, charge q, you know that each of these has charge q and minus q, and mass m, they similarly expect you to assume that this has mass m, this also has mass m. That's why I've given that as part of the question, okay? Now, with that assumption, let us try and see how to solve this question. So this is the electric field. The dipole has been rotated slightly with respect to the electric field. So theta is small. So we can say sine theta approximately theta. Now, When you have the dipole like this, you know that the torque is going to be in this direction, right? The torque will be like that. That will be the torque direction. But the direction that is positive is the theta direction. So we are going to take this as the positive direction. This is the positive direction. So what is the torque? P is sine theta with a minus sign. P is sine theta with a minus sign. So tau is P cross E, but I'll just use the direct value. Pe sine theta, but that is in this direction, that is the positive direction, so put a minus sign. And this is approximately minus Pe into theta. Why? Because sine theta is approximately theta, so minus Pe into theta. Now this must be equal to I alpha, so this must be equal to moment of inertia of the dipole into alpha. Tau equals I alpha, you know that from rotational dynamics, right? So Newton's second law for rotation, just like you have F equals ma, here you have tau equals I alpha. Alpha is theta double dot. So I will use this convention, alpha is theta double dot. So from this we can write theta double dot is minus Pe by I theta, right? So theta double dot is minus Pe by I into theta. And so this must be, right, this must be omega square. So we can write that angular frequency omega, this is not angular velocity, it's angular frequency, frequency of oscillation, right? Angular frequency is root of Pe by I. Because theta double dot is equal to minus omega square theta, so omega square must be Pe by I, so this must be omega. So far all clear? Okay, and time period, because here they have asked you what? Time period of oscillation. So time period is 2 pi by omega. We just looked at this anyway. I'm just redoing it so that you know it. This is how you will calculate. So 2 pi. Every time my recommendation is that you write down the torque, say that it's equal to I alpha, then write this. Don't remember it like a formula. Okay, so then 2 pi root of I by Pe. So all that is fine, but I need P. E of course is E naught, so that's not a problem. What about P? P, dipole moment, is Q into L. Length L is given, charge is Q, so Q into L, Q into L. Is it 2QL or is it just QL? The 2QL that you generally learn from the NCERT textbook is because they take this length as 2L. If this length is 2L, then it will be 2QL, right? L, Q into the distance. Q into the distance. Here the length is L, that's all. So Q into L. Okay, keep that in mind. This is Q into L. Okay, what about I, moment of inertia? Moment of inertia will be this mass, right? You always take it about the center so that you can then say that this length is L by 2. This length is L by 2. So M into L by 2 whole square, right? L by 2 whole square. What is that? L square by 4. So M into L square by 4. And for this also you have M into L square by 4. So plus M into L square by 4. And so that is going to give me 2 times M into L square by 4, M into L square by 2. This is the moment of inertia. So I know P, I know I. That's all, just simply substitute. You've got it, right? So time period is 2 pi root of I, so ml square by 2, ml square by 2 divided by Pe. P is QL, QL, E is E naught. Okay, now this L and this L square you can cancel out, one L, and so you get ml by 2q E naught. Okay, so you have 2 pi root of ml by 2q E naught. Is there an option like that given here? No, 1 by 2 pi, no. 2 pi ml by q E naught. No, that is not it. Look at this one. 2 pi root of ml by 2q E naught. So the correct answer is option C. So I hope this is clear. Very simple, straightforward question if you know the basic principle of dipole oscillations. Okay, it's very important to know this because you're going to keep getting questions like this. So once you know it, the questions are actually quite easy. Let us now look at another question like this. I'm not going to do this question, but let us read this question that appeared in the JEE in 2019. It is exactly the same as the previous question. That's why I'm not going to do it. This is homework for you guys. Okay. So an electric dipole is formed by two equal and opposite charges Q with separation D. The charges have the same mass M. So like we saw earlier, right? So you have a plus, you have a minus, you have Q here, you have mass M, you have minus Q here, mass M, and this is placed in an electric field. Okay, it is rotated slightly and released. Exactly what you're going to get, except this length is called D now. That's all. Right? So you can easily solve this question. Exactly the same approach as we did earlier. I'm not going to do this. Please do this yourself as homework. Okay? Instead, let us focus on a slight variation, because this question is exactly like the previous one. I'm not looking at that question now, but I'm now going to look at this question, which is slightly different. And many people make mistakes unnecessarily here. This appeared in the JEE in 2023. Okay. What is the big difference here? Here also you have this dipole. A dipole comprises of two charged particles of identical magnitude Q. The charges are plus Q minus Q. Identical magnitude, opposite in nature, basically plus Q minus Q. The mass M of the positive charged particle. Notice, read this carefully. So the positive charged particle has mass M, and this mass is half the mass of the negative charged particle. So if this is half of this, this must be 2m. If this is m, this has to be 2m. That is the variation. Small variation, but an important variation. Okay. The two charges are separated by a distance L. Not 2L, L. If the dipole is placed in a uniform electric field E such that it makes a very small angle with the field, find the angular frequency of oscillations of the dipole when it is released. Okay. So how do I do that? Well, we are going to take this direction as being the positive direction. This is the positive direction. You know that the torque P cross E is going to be this way in this position. This will be the direction of the torque. So it has to be negative, right? The torque has to be negative. So tau is PE sine theta with a minus sign, but sine theta is approximately theta. Why? Because it says it's making a small angle. So theta is small, so sine theta is approximately theta. So I can directly write minus PE sine theta. I will just substitute theta instead of that. And of course, this is not equal to, this has to be approximately equal to. So this is tau, but tau equals I alpha. So that tells us theta double dot is minus PE by I theta. Okay, so theta double dot. See this, I'm writing some extra steps, but it is worthwhile because next time something changes, I becomes different, etc. You will know exactly how to calculate. So always start from the fundamental equations. So theta double dot is minus PE by I theta. So this must be omega square, and here we are only interested in omega, angular frequency. So what do we want? We don't want the time period. So it is just root of PE by I. This is what we want. Except I need to calculate P, I need to calculate I. E, of course, we know. E, we know. Okay, uniform electric field E, not even E naught, just E. So I'll just use E. Okay. Okay, first P. Q into L. Please remember, it is not 2Q into L, it is Q into L in this case, because they have given the length as being L. Look at that. The distance is L. Okay, depending on what they give in the question, you have to use that. Okay, what about I? Moment of inertia. M into L by 2 whole square, which is L square by 4. 2M into L by 2, right? You're taking about this point, right? So L by 2 whole square here will be L square by 4. So let me write moment of inertia carefully. This is the most important part. M into this square. M into L square by 4 plus 2M into L square by 4. 2M into L square by 4. We are taking everything about the center. Torque about the center. We are taking the, well, in this case, overall torque will anyway be that only, couple. But we are taking it about the center. And so moment of inertia also, we are taking it about the center. So if I now look at this, this will be 3 ml square by 4. 3 ml square by 4. And if I take this I and I substitute it in here, I'll get what is omega. So let us calculate omega. Omega is root of P, which is QL, E, which is just E, right? In this question, it is just the electric field E, divided by I. Divided by I is 3 ml square by 4. By 4. So by 4, I'm going to take the 4 up there. One of these L's will cancel. And so I'm going to get root of 4QE by 3 ml. Root of 4QE by 3 ml. Is there an option? Yeah. Root of 4QE by 3 ml. So this is the correct answer. Okay. Root of 4QE by 3 ml. That is not right because that doesn't have a 3 there. And these, of course, are clearly not right. So root of 4QE by 3 ml. Why have they given these options? For example, who will make this mistake? People who remember dipole moment formula from the NCERT textbook is 2QL. If you remember it that way, instead of remembering it as charge into the distance between the charges, if you remember it like a formula and you use 2QL, then what would have happened? Here you would have put 2 more, right? 2QL. You would have ended up getting this. This is a trick option. They have given this option for people who will make a mistake here. Okay. The formula in your NCERT textbook is different. I mean, that's a good formula, but there this length is 2L. Here the length is L. So you have to write these things carefully. Don't just remember whatever the formula said there. Please calculate it carefully and then you will get this as the answer. So I hope this is clear to you. So you can see once you have understood how to solve dipole oscillations questions, these questions are all actually quite easy. 2 steps, 3 steps, you'll be able to solve them. Okay. These are all JEE questions and they will keep coming up in JEE. Now I have done one of the type of questions that will come up, right? But there are many, many more types of questions from the electric charge and field chapter. And so I have done an entire course. This course, class 12 course, electric charge and field, this has 6 skill builders, 114 concepts and solved example questions. Each of the solved example questions will take up one important type of question and help you understand how to solve it. Okay. This is a very useful course that you can look at. All the concepts and all the question types that you need from this chapter will be explained in this course. You can go to the AhaGuru Courses app from Google Play Store, download that and you can see this course there. You can then get it from there. Or you can go to ahaguru.com/microcourses. You go to this website and you can take this course. This is one single chapter alone that you can easily go through. You will find that this is going to be super useful for not just your 12th standard, CBSE as well as ICSE, but also for JEE and NEET. Okay, all your concepts will become super clear and you will be able to solve any type of question that will come up. And if you use the code, because you are on YouTube, if you use the code YT15, you will get an additional 15% discount on this course. So please do take it up and see. You will find that it's extremely useful. See you all next week with another type of question. Okay, bye.